Assalamu alaikum everyone, and we are about to start our last lecture on power electronics EEE 4227. And in today's lecture, we are going to talk about AC drives. That means the driver circuit which are going to be used to control the speed of AC motors. And if we look into the introduction slide, you can see that these AC motor drives are largely used to control the uh, control defined applications of AC motors. And if you talk about power system load, 70% of this load is actually induction motors. So we'll be talking about the driver circuit for induction motors, but definitely there are some synchronous motors as well where you can control the speed using these different AC motor drives. And the question is, why are we going to use these AC motors almost everywhere? Because you find that these AC motors are with low maintenance because they don't have any brush or commutator setup like you had with DC motors. So in that case, these AC motor will have a longer lifetime, and because of the lack of these setups like commutator setups or brush setups, you can see that the same rating of these two motors, like DC motor and AC motor, when you compare them, you will find that the AC motor is having a lighter weight, like 20 to 40% lighter than equivalent DC motor. And because it doesn't demand that much amount of maintenance, so you can say that these motors are usually inexpensive. The problem with AC motor is the working principle is little bit complex compared to DC motor, so it takes some time to understand the whole thing. And the power control is also a little bit complex in comparison to DC motors. In DC motors, we had some straightforward equations, and those equations were showing the relationship in between speed and the controlling parameters. But in this case, you will find that you need to plot the torque and speed characteristics curve, and then only you can find that how the controlling parameters are varying the torque and eventually varying the speed. Okay, so the relationship is not that simple, little bit complex. So we'll go through the torque speed characteristics plot and try to find out the parameters which will be used to control the speed. First, the torque, and then the speed of different AC motors. Now, the AC motors we actually think of, or we are actually concentrating in this lecture, is basically induction motor. Okay, so talking about induction motor, this was the equivalent circuit for induction motor. You can see that induction motor is nothing but a transformer having the secondary shortage. Okay, that was actually induction motor. So if you think of a transformer with a shorted secondary, it would have a equivalent circuit like this, where this is your primary side and this is your secondary side. Your secondary is basically that rotor. We actually short that rotor terminal. That's it. Okay. So this is your rotor side and this is your stator side. But to solve any mathematical problem or to have simpler analysis, we try to bring the secondary side to primary side. So when you bring the secondary side to primary side, that means rotor circuit to stator circuit, then you will find that the circuit would look like this. Okay, so in this circuit, we because we have taken the secondary component into primary side, so there is a little bit of conversion, and eventually you can see that the circuit should look like this. So where you have stator resistance, stator reactance, rotor resistance taken to primary side, rotor reactance taken to primary side, and we had these two elements like magnetizing reactance and core losses, resistance representing core losses. But because that resistance is quite large, so we actually take it as an open circuit. So if you think of this connection as open, then you are actually left with this type of equivalent circuit. Okay, so you have xn, you have xs, rs, and all these stuff. So this is your ultimate equivalent circuit for an induction motor. Okay, and if you try to develop the torque equation for induction motor, the torque equation will be something like this: torque is equal to developed power divided by speed. You all know that developed power is nothing but the product of torque and omega. So we are just writing it the other way. So developed torque is actually PT divided by omega. And find the expression of developed torque in terms of this equivalent circuit parameters, then the expression would look like this. You can see that the parameters inside this expression are all coming from this equivalent circuit: rotor resistance, stator supply voltage, and then omega is the synchronous speed, slip is for this induction motor, and you have RS as well, XS, XR, all these are present, and they are coming actually from this equivalent circuit. Now, this is your developed torque, expression of developed torque. Now, for this expression of developed torque, if you try to plot a curve in between, or if you try to plot the relation in between speed and the developed torque, the relation would look like this, the black curve. Okay, that actually shows the relation in between the developed torque and the speed of a motor, of an induction motor. Now, for an induction motor, you can see that initially there is the omega m, initially the omega m, or the mechanical speed, or the speed of the rotor, that is 0. Okay, initially it is 0. So if it is initially 0, then when you count the slip at initial condition, then the slip should be equal to 1, because initially your omega m was 0. So we are right at this point where the rotor speed is 0, and you can see that the slip is actually 1. So if my slip is 1, in that case, I put that value s is equal to 1 in this expression, and you will find certain value of Td. Okay, so that is the value of developed torque at starting point. So I can call that Td as T starting, because that is the developed torque in the at the starting moment. Okay, so this is TST. Okay, so how do you calculate the TST? Just by placing s is equal to 1. Okay, and now you slowly increase the value of s, as it decrease the value of s, because initially s is 1. Okay, and then you continuously increase the speed. I mean, this one continuously increases, this omega m continuously increases, and s decreases. All right, eventually at the end point, what you do is the machine is actually locked, and when omega s is equal to omega m, that will never happen actually. But if it happened, then it would look like this, the plot should look like this. But at certain point, the torque, I mean, the torque continuously increases, and at certain point, it will reach the maximum value right here. It will reach the maximum value. So how to get the value of maximum torque from this plot? To get the maximum value of torque, what you expect here is, on x-axis you had slip, on y-axis you had torque. Okay, so at this point, the slope of this torque with respect to slip is 0. Okay, so if I put that expression like the maximum point, for the maximum torque to achieve, we put dTd with respect to ds is equal to 0. In that case, you can get an expression for s, which is s max, which I call s max, that is related to the torque maximum. And if you put this s max, this expression, in the expression of td, then you come up with this expression for maximum torque. Okay, so this is the expression for maximum torque. So where are you going to get this value? You are going to get this value right here, that is t max. And for which slip this is actually occurring? This is occurring for s max. Okay, so the expression for s max and t max all are given right here. Okay, and how do you get that? You get that by putting this value dTd ds is equal to 0. Now these are all for a motor, induction motor, which is running as a motor. Okay, now the question is, can a motor run as generator? The answer is yes. An induction motor can run as generator. Now when this induction motor is going to run as generator, that is the next question. But before getting there, let me explain one more thing. We actually didn't talk about this red curve here. There is a red plot right here. So what is that red plot for? That red plot is showing the mechanical load that you put on the shaft of the motor, induction motor. All right, so depending on what load you put on your shaft, this is going, I mean, the speed, the final speed is going to be decided. Okay, so you can see that this was the free running plot for torque and speed curve of the motor, and you put the certain mechanical load on top of that shaft, so that actually cross this free running plot at certain point. So where is that, I mean, where is the cross section point? Right here. Okay, so you can see that if you try to get the speed for that particular load, speed will be something like this right here. Okay, so you get the actual speed and the corresponding torque right here. This is showing the corresponding torque. Okay, so this is the way to get the final torque and speed of a motor when it is running with certain load, certain mechanical load. Now the next question is whether the motor can run as generator or not. Yes, the motor can run as generator. So we are familiar with this part. If you check this plot, you can see on x-axis we have slip, on y-axis we have torque. Okay, so initially when your slip is one, means you are right here. You have certain starting torque. Okay, and that keeps on building, and finally it reaches a maximum value, and then it again falls to zero value. Okay, and at this point this is actually the locked condition. At locked condition, s is equal to zero because your omega m is equal to omega s. That's why this is becoming zero. So up to this point this was behaving like a motor. So this portion of the plot, this is for induction motor. Now when the motor is running as motor, or when the induction machine is running as motor, you can expect that your slip is somewhere in between 0 and 1. Okay, it is positive because your omega m is always less than omega s. If I say this is omega s and this is omega m, then I can say that omega m is always less than omega m is always less than omega s. Okay, so what happens here is because this omega m is always less than omega s, so your slip should be somewhere in between 0 and 1. All right, and next is, what about for this region? I assume that my shaft, I mean the shaft, the rotor shaft we are talking about, that shaft has been or is running with an external force. An external force could be a wind turbine. Okay, wind. Okay, so a wind, some sort of blowing wind is actually running that turbine. Okay, so the turbine shaft is actually rotating, and when it is rotating at a speed that omega m is coming up with a value which is greater than omega s. Okay, so how this is happening? Because you are running that shaft or running the turbine with some sort of external force. So you are giving some mechanical input, and eventually you will find that the machine is somewhere connected to the grid. So you will find that this machine is actually injecting some amount of power into the grid. It is no more consuming as a motor, rather it is actually supplying power to the grid. So it is behaving like a generator. So when it is behaving like a generator, what should happen to the value of its speed? Sleep. By this time we know that this omega m is now greater than omega s. So when omega m is greater than omega s, obviously sleep will be negative. Obviously sleep will be negative. So at this point we can say sleep is negative. And when the sleep is negative, if you go through these equations here, say for example, talk about this equation. If your sleep is negative, your torque is negative, your developed torque is negative, and your power is negative as well. So this is an induction machine. This is supposed to be running as a motor, but when it is showing you a developed power with a negative polarity, that means what? This is no more a motor. This is a generator. Okay, and it is feeding power to grid where it is connected. So you can say that at this point, right in this region, your omega m is greater than omega s, so that results in negative sleep, and your torque is negative. And because your torque is negative, you are producing some amount of power, real power, and you are injecting that real power into the grid. So this is called forward regeneration mode. And the last region to discuss about is reverse plugging. So what is this reverse plugging? The last region is about this one. You can see that the slip starts from 1 and it goes up to 2. So what is that range? I mean, in this case, you can see that omega m and omega s, they don't rotate in the same direction. The direction of the rotation is completely opposite. So how do you ensure that? I mean, how do you ensure this opposite? These two speed, these two rotations, they are in opposite direction. How is it possible? The one that is the mechanical speed, that is the rotary speed, right? And the other one is the virtual one, which is synchronous speed, and this is created by, because this is a three-phase machine, this is created by that ABC connection, right? That stator connections. If you alter that connection, you make that connection, instead of ABC, you just reverse the connection or change the connection to ACB. What will happen? It will simply reverse the direction of rotation. So the virtual field, that virtual synchronous field that was created by the connection of that three-phase terminals of stator, you can easily change the direction just by changing that connection. So when your omega s is in opposite direction to omega m, what will happen? In this case, you will find that your slip is greater than 1, okay? And the motor will find opposite polarity torque, not opposite polarity torque, it senses opposite field, so it tries to go through plugging. We usually try to avoid this sort of plugging, because in this case what happens that there will be excessive amount of heat produced in the windings. Okay, so we try to avoid this sort of plugging, but it is still there. I mean, this is definitely one reason where you can get slip above 1. So these are the three regions of operation. Okay. Now the question is, whatever we have discussed so far, these are all about induction motor. Now, if you are asked to find out the ways to control the speed of induction motor, what will be your answer? Your answer should be, first of all, try to find out which parameters are going to influence the torque, the developed torque. If you can find out the parameters which are influencing the developed torque, then you know that the speed is going to vary according to that developed torque. And you are going to follow this plot. Okay, so if you know the amount of torque is somewhere here, you know the speed should be somewhere here. Okay, and that's how you can find out the new speed. So we have got a nice expression for torque. The nice expression for torque was like this. Okay, now try to find out what parameters can you vary to vary this torque. And when you vary torque, eventually you vary speed according to that plot, that torque speed plot. So what are the parameters we can vary? First of all, the thing you can vary is supply voltage. Supply voltage means stator voltage. Okay, you can vary stator voltage. Eventually, this torque will vary. Very much clear, right? The next thing you can vary is stator frequency. You can see this omega is here. Okay, this is nothing but the stator frequency. All right, so you can vary the frequency or stator frequency to control the torque of the motor. The next thing you can vary is this RR prime. It's not always possible, especially for squirrel case, this will not be possible. But if it is an owned rotor machine, in that case, you can include some new resistance in the rotor circuit. There is some scope. All right. So in that case, you can control the resistance of the rotor, or it is called rotor voltage control, through which you can control developed torque. And there are a few other steps as well, like you can combine the voltage and frequency together and eventually control the torque. Okay, so if we try to find out the techniques through which I can control the speed of induction motor, these are the techniques you can summarize: stator voltage control, stator frequency control. You can combine both controls together to have a precise control, like stator voltage and frequency control. Then rotor voltage control, stator current control, and voltage current and frequency control. So there are many different approaches. Now we'll go through the first 4 approaches. In fact, we are going through these 1, 2, and 4. These 3 approaches. How do they actually work and control the speed of induction motor? So the first approach is stator voltage control. If you look into the equation, this was the equation, developed torque equation. And if you look into the plot, this was the plot right here. So you can see that if we vary that stator voltage, we are going to, we are going to control or the torque is definitely going to be controlled or varied according to that stator voltage. Now, can you apply certain stator voltage above the rated voltage? The answer is no. Okay, you cannot apply certain voltage above the rated voltage, right? The supply voltage cannot be beyond a certain limit, which is already mentioned somewhere in the specification or nameplate. So you can see how, I mean, if you are asked to find out the ways to control the voltage, the supply voltage to stator, what should be the control mechanism to control the voltage of the stator or the supply? First one is AC voltage control. The next one is voltage fed variable DC link inverter or PWM inverter. So this is basically, these two are basically the same thing, and this is achieved uh, through some back-to-back connection of rectification and then inversion. Okay, so the first one, AC voltage controller, we have already gone through AC voltage controller, and we know that how to control the AC voltage on output terminal. You know how these AC voltage controllers actually work. And then you also know the next part as well, where you talk about rectification first, and then rectified output is made made AC after certain inversion. Okay, so both are already known, and we know that this is how we can control the output voltage. So eventually, if you can control the output voltage, if you run the motor at a certain lower supply voltage, what will happen? See this one, the green plot and the blue plots. Okay, in this case, you can see that we are running the motor at a lower supply voltage than the rated one. The black one is the rated one, and the last two are the voltages which are lower than the rated values. So you can see if this is your mechanical load torque, then it actually crosses these three plots at three different cross sections, right? So this is one, this two, this is three. Okay, these three different cross sections. So if you are running with supply voltage, the rated supply voltage, then you are coming with this omega. If you are running at a lower supply voltage, you are coming with a lower speed, omega 1, and even lower than omega 1, which is omega 2, with a supply voltage lower than the second one, VS1. Okay, so this is how you can see that we can control the supply voltage and eventually control the speed of an induction motor. The next thing to control is frequency. Okay, in this equation you can see that we had omega s, so you can easily control the frequency and again expect some changes in torque and eventually in speed. So what will happen when you control the speed? How to control the speed? Through the change in frequency. We can change frequency uh, in with two different approaches. One approach is cycloconverter. We can use cycloconverter. Okay, you know cycloconverter, you have cycloconverter with both options. It can increase the frequency, it can decrease the frequency. You have both options, so either of these two can be used to get variation in frequency, and when you vary the frequency, you can see that there should be some changes in torque and in speed as well. Now the question is, are you going to decrease the frequency? See this one, if you can decrease the frequency, you can expect certain increase in torque, right? But we usually don't go for that option. We usually don't decrease the frequency, rather we increase the frequency. The question is why? Why don't we decrease the frequency and run at a different speed than the rated one? The answer is right here. You can see that if you decrease the frequency, it will decrease the value of XS and XR. All right, if you decrease the frequency, it will reduce the values of this XS and XR. That will result in increased current flow through the coils, which might not be tolerable. Okay, which might not be within the tolerable range. In that case, it will simply burn the coils. So it's better to go for higher frequency operation. So when you go for higher frequency operation, the plot should look like this. You can see that if your frequency is simply equal to synchronous frequency, the plot is like this. If you increase the frequency to 1.5 times, the plot shifts like this. If the frequency is 2 times the supply frequency, then it's something like this. So now, if you draw the plot of load curve, it will definitely, it should not be greater than the starting torque, should not be greater than the default starting torque. So it should cross the free running plot at certain point, and you can eventually find the ultimate speed of the what is it, the motor, the induction motor. Okay, so this is how you can change the frequency to certain level and uh, run the motor at a new speed. Next is the last approach, which is called induction motor speed control using rotor resistance. So rotor resistance, you can have scope to change the rotor resistance only with owned rotor induction motor. Not possible with squirrel cage one, okay? Because you don't have any scope to introduce any new element for squirrel cage rotors. But in this case, when your rotor is an own rotor induction motor, you can introduce resistance on all three phases like this, okay? And you can see that if you change the resistance, see this one, your resistance was right here, here as well. Okay, so when you are changing this resistance, the change in torque is appearing like this. Okay, so this is R1, this is R0, this is R2, and as you keep on increasing the resistance, you can see that your starting torque continuously improves. Okay, and the plot actually changes like this. But to change the resistance in all three phases uniformly is a challenge. Okay, so change the resistance in all three phases uniformly, this is definitely a difficult task. So to address that issue, we are actually introducing this type of arrangement where you can see that rotor resistance is passed through full wave rectification, and when it is passed through full wave rectification, you have a register as a load for that full wave rectifier. Now this register is, I mean, is not actually always, I mean, it is actually not counted all the time in the circuit because of the presence of this GTO. If you turn on this GTO, this register will not be counted, rather it will be counted as short. It's short circuit, okay? So this will be simply shorted when you turn on this GTO. And if you turn off this GTO, then only this circuit finds that there is certain amount of resistance. So you can see that all three phases, they are actually finding the same resistance, but that resistance is what we call effective resistance. And that effective resistance is only present when you turn off the GTO. Otherwise, it is not present. So if the duty cycle to turn on the GTO is K, because the resistance appears only for the turn off duration, that's why we call effective resistance is equal to R into that turn off duration 1 minus K. That is the effective resistance that is going to be sensed by this own rotor induction motor. Okay, so that's how you control the speed of induction motor, and in this case you don't need to worry about uh, non-uniform variation in R, because you have only one R here, and this is always uniform variation, and this is quite precise because you can change this K continuously. So that is actually the end of these AC motor drives. One more point to discuss is this part, this frequency control. This is largely applied in recent years. Okay, largely applied in recent years. You will find that we are using adjustable speed drives or variable frequency drives in many applications. The question is why? Why are we actually leaning towards this variable frequency drive or adjustable speed drives? The answer is, in case of variable frequency drive, you are using different frequency to achieve different speed. In many cases, you will find that you do not need to run the motor all the time at full rated speed. Okay, so if you do not run the motor at full rated speed, what happens? That if you, I mean, is there any improvement in terms of power consumption or in terms of efficiency? The answer is yes. You will find certain improvement in efficiency, especially in efficiency, when you are running the motors at a speed lower than the rated speed. So that is what we are showing right here. We can see that the speed of fan or pump, if it is running at rated speed, okay, rated speed, 100% rated speed, then the mechanical power required will be simply 100%, simple. But if you're running the pump at 90% speed of rated speed, then the mechanical power required is 73%. You're actually saving 27% just by reducing the speed by 10%. See this one, if you are running the motor at 50% speed, your power requirement will be simply 13%, only 13%. So you are actually saving 87% of power. Okay, so that means just by running the pump or fan at a speed little bit lower than the rated speed, you can save huge amount of power. That eventually improves the efficiency. That's why we are leaning towards this frequency control setup of different AC motors, and that actually results in huge savings in terms of energy, and definitely it's saving your bill as well. Okay, so we are actually leaning towards this type of circuit. You can see that we have summarized this um, this gain or these features, these advantageous features of using VFD or ASD in AC motor drives. And this is the circuit we are talking about. You have initially you do some rectification, okay, and after doing rectification, you can change the frequency to any value. Like not necessarily it has to be at 50 hertz or 60 hertz. It can be at few hundreds of hertz, okay, 2 times or 3 times of frequency than the supply frequency. Because in that case, you can reduce when you have scope to change the frequency. You can change the speed. So if you can run at lower than the rated speed, you can save some energy, and that will result in energy saving operation or energy efficient operation. So that's why in recent years you will find that most of the AC motor drives, they are implementing this kind of VFD setup. Okay, and well, that's all for today's class, or the other way, that's all for power electronics course. Now, any question from your end? প্রশ্ন থাকলে করো। তোমাদের কোনো প্রশ্ন আছে কিনা? প্রশ্ন নাই নাকি?
স্যার আজকের ক্লাস রিলেটেড নেই, বাট অন্য কিছু নিয়ে আছে।
আচ্ছা, তাহলে আজকের ক্লাসের অ্যাটেন্ডেন্স এর লিংকটা আমি দিয়ে দিই আগে। হ্যাঁ, অ্যাটেন্ডেন্স লিংকটা দেওয়া আছে, অ্যাটেন্ডেন্স লিংকটা কালেক্ট করো, ওখানে জাস্ট যে ফিল আপ করে সাবমিট করে দাও। আর কি প্রশ্ন ছিল?
স্যার আমাদের এবার এক্সামটা স্যার কিভাবে কন্ডাক্ট হবে স্যার ফাইনাল ইয়ার?
আর তো কোনো নোটিশ আসছে নাই। নোটিশ আসছে কিছু?
না স্যার, মানে আর 1 উইক আছে তো এর জন্য জিজ্ঞেস করছিলাম।
আমার মনে হয় এই 1 উইকের ভিতরে নোটিশ আসুক, আমাদেরকে কিছু জানানো হয়নি। নোটিশ আসলে তখন তোমরা যখন জানবে আমরাও তখন জানবো।
স্যার ওই যে অ্যাসাইনমেন্টটা বলছিলেন যে টার্নিটিনে চেক করতে, এখন স্যার টার্নিটিনে তো আমাদের শুধু হচ্ছে ল্যাবের সময় ল্যাব রিপোর্ট গুলোর জন্য এক্সেস দেওয়া থাকতো, এছাড়া তো আর কোনো এক্সেস দেওয়া নেই। তাহলে ওইটা কিভাবে করবো?
ল্যাব রিপোর্টে তোমার যদি এক্সেস দেওয়া থাকে তাহলে সেম অ্যাকাউন্ট দিয়ে তুমি এটাও চেক করতে পারবে, সমস্যা নাই। আর যদি তুমি মনে করো যে আমি সেপারেট অ্যাকাউন্ট ক্রিয়েট করে দিব আর সেপারেট অ্যাকাউন্ট ক্রিয়েট করে দিতে পারি, তাতেও আমার কোনো সমস্যা নেই। আমি তাহলে ক্লাসরুমটা দিয়ে দিব, তোমাদেরকে একটা অ্যাকাউন্ট দিয়ে দিব, ওটা লগ ইন করে ওটার মাধ্যমে শেয়ার করবে, ওটার মাধ্যমে চেক করে নিও, কোনো সমস্যা নেই।
ওকে, থ্যাংক ইউ।
ল্যাব রিপোর্ট যেটা দিয়ে চেক করো এটা দিয়েও চেক করলেও কোনো সমস্যা নেই। আমার মনে হয় ল্যাবের যিনি ক্লাস নেন কোনো কিছু মনে করবেন, মনে করার কোনো কারণ নেই, তাই না? তারপরে আমি দিয়ে দেবো, সমস্যা নেই। আমি তোমাদেরকে আজকে অথবা কালকে আমি চেষ্টা করবো অ্যাসাইনমেন্টটা আপলোড করে দিতে। তোমরা 7 ডেজ মিনিমাম টাইম পাবা, নেক্সট উইকের ভিতরে জমা দিয়ে দিবা। এটা একটা বিষয়। আর একটা হচ্ছে যে আরেকটা ফর্ম আমি দেওয়ার কথা বলছিলাম তোমাদেরকে, সেটা হচ্ছে আমাদের যেহেতু আউটকাম বেসড অ্যাক্রিডিটেশন নিয়ে আমরা কাজ করি, ইউনিভার্সিটি মানে প্রোগ্রামগুলো অ্যাক্রিডিটেশন একটা বিষয় থাকে, তো সেইটার জন্য একটা ফর্ম তোমাদের ফিল আপ করতে হবে, সেটা হচ্ছে কোর্স ফিডব্যাক ফর্ম। তো ওই ফর্মটা আমি তোমাদের দিয়ে দিব। 4টা সিও ছিল আমাদের কোর্সে, মানে কোর্স আউটকাম ছিল 4টা ভাগে ভাগ করা ছিল আসলে পুরো কোর্সটা। তো তোমাদের মানে এই প্রতিটা কম্পোনেন্ট তোমরা কিভাবে বুঝছো বা তোমাদের এক্সপিরিয়েন্স কি বলে, সেটা থেকে তোমরা ওইখানে জাস্ট কিছু মানে কয়েকটা ঘর আছে আর কি, জাস্ট এক্সিলেন্ট, স্যাটিসফ্যাক্টরি, এই টাইপের কয়েকটা ঘর আছে, জাস্ট ওখানে তোমাদের রিমার্কটা দিয়ে কমপ্লিট করে দিবা। এটা কিন্তু মানে আমরা এক্সপেক্ট করি যে মোর দেন 80% স্টুডেন্ট এটা কমপ্লিট করবে। ওকে, সো ওই অনুযায়ী আমি দিয়ে দিব, সবাই এটা কমপ্লিট করে দিবা প্লিজ, কারণ এটা তোমাদের প্রোগ্রাম যাতে সুন্দরভাবে রান করে সেটার জন্য এটা প্রয়োজন। আর কোনো প্রশ্ন?
স্যার নেক্সট উইকের ক্লাস 3টা।
নেক্সট উইক আর কোনো ক্লাস হবে না, আজকে লাস্ট ক্লাস।
ওকে।
এরপরে যেটা হচ্ছে যে আমাদের ইউনিভার্সিটি থেকে নোটিশ আসলে পরে যে এক্সামের মানে ফর্মটা কিরকম হবে সেই বিষয়টা, ওই গাইডলাইন আসলে পরে তখন আমি তোমাদের যদি কোনো কোয়ারিজ থাকে, বিশেষ করে তোমাদের যে কোয়ারিজটা থাকবে সেটা হচ্ছে আসলে প্রশ্ন রিলেটেড, যে প্রশ্ন মানে কয় সেট হবে বা সেখান থেকে কয়টা উত্তর করবো বা কি, সেই জিনিসগুলো আমি পরবর্তীতে তোমাদেরকে ক্লাসরুমে তোমাদের সাথে শেয়ার করবো, একটা গাইডলাইন দিয়ে দিবো।
ওকে।
তো তাহলে আজকে আমরা এখানে শেষ করি। তোমাদের কি রুটিন ঠিক হচ্ছে, মানে কবে পরীক্ষা দিচ্ছ?
স্যার ডেট তো দিয়েছে মনে হচ্ছে, কিন্তু পুরোপুরি এখনো কনফার্ম না।
পাওয়ার ইলেকট্রনিক্স পরীক্ষাটা কখন নিচ্ছ তোমরা, কি সবার শুরুতে না?
না স্যার, আমরা এখনো স্যার ডিসকাস করিনি ওটা, যে কোনটা কখন।
আচ্ছা, পাওয়ার ইলেকট্রনিক্স এর কন্টেন্ট যেহেতু অনেক বেশি, আমি
বন্ধ রাখবো।
সেটা হচ্ছে শুরুর দিকে নিয়ে নেওয়াটাই ভালো, কারণ অনেক সার্কিট তো।
জি
সার্কিট পরীক্ষার আগে যে একটা পর্যায়ে যে মনে হয় যে সব সার্কিটই একরকম, প্র্যাকটিস করলে অবশ্য সেটা থাকে না, তবে প্র্যাকটিসের জন্য পর্যাপ্ত সময় রাখবা, সেটাই বলা হচ্ছে। ক্লাসে যেগুলো পড়ানো হচ্ছে আমি চেষ্টা করছি সবগুলো লেকচার আপলোড করে দিতে। এসি মোটর ড্রাইভস এর লেকচার আমি আপলোড করে দিব ইনশাআল্লাহ, এটাতে এখনো আপলোড করা হয়নি। আর কোনোটা যদি মিসিং থাকে, তোমরা যদি মিসিং পাও যে স্যার কোনো একটা লেকচার আমি পাচ্ছি না, রেকর্ড পাচ্ছি না বা কিছু, আমাকে জানালে পরে আমি চেষ্টা করবো ওটা আপলোড করে দিতে, কোনোটা যদি মিসিং থাকে।
ওকে।
তো তাহলে সবাই সুস্থ থাকো, ইনশাআল্লাহ কথা হবে, ভালো থাকো, আল্লাহ হাফেজ।
ডকুমেন্টস।
ওয়ালাইকুম আসসালাম।
আসসালামু আলাইকুম স্যার।